this lecture, we continue our discussion on the travelling salesman problem. We look at heuristics to solve the travelling salesman problem. Now, first we have to look at what a heuristic is, and then we try and explain why we provide heuristic solutions to the travelling salesman problem. Now, the first question is, what is a heuristic solution to this problem? In the earlier lectures, we had seen three types of branch and bound algorithms to solve the TSP. All of them gave us the exact solution, which is shown here. The exact solution being 1, 3, 4, 2, 5, 1 with z equal to 34. Now, this exact solution tells us that the best value or the minimum cost solution is 34, and the person travels from 1 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1 with z equal to 34. All the above branch and bound algorithms were able to give us this value with z equal to 34. Now, the three branch and bound algorithms we had solved using this example of a 5-city travelling salesman problem. We have already seen that for a n city problem, we have n minus 1 factorial feasible solutions, out of which the best one is with 34. So, for the 5-city problem, we have a maximum of 4 factorial feasible solutions, and if we look at a 20-city problem, then we might even go to as high as 19 factorial feasible solutions. Now, when we apply the branch and bound algorithm, any one of the three methods that we have seen, and let us assume that we would choose the third branch and bound that we saw in the earlier lecture. Now, when we apply these branch and bound algorithm to large problems, large meaning of the order of 100 cities or more, in fact 100 is not seen as a very large problem, but if we apply it to a 100-city problem, then we will observe that the number of nodes is very high, the CPU time taken is also very high, and it may not be able to solve a 100 factorial problem within a reasonable computing time or within a reasonable CPU time. Now, that happens because of the exponential nature of the travelling salesman problem. Now, this leads us to a discussion on the complexity theory. Now, the branch and bound algorithm that we have seen comes in the category of an exponential or a non-polynomial algorithm, where the computational effort taken is not described as a polynomial function of the problem size. Any branch and bound algorithm in the worst case can evaluate all possible solutions, which means for a n city travelling salesman problem, it might end up evaluating n minus 1 factorial solutions, which is an exponential number. So, wherever for whatever problems when we do not have algorithms that have what is called a polynomial complexity, branch and bound is a non-polynomial complexity. Wherever we have algorithms that do not run in polynomial time, then it becomes necessary to get good solutions. Good solutions, not necessarily exact, but to get good solutions with algorithms that run in polynomial time. Now, heuristic algorithms actually provide us with all these three things. Every heuristic algorithm attempts to find a good solution to the problem, does not guarantee exactness. Sometimes we may get the exact solution, many times we may not. most importantly gets quick solutions in terms of computational time and effort. It is polynomial time and effort, and they are mostly quick with respect to providing these solutions. While branch and bound might take an exponential or a non-polynomial amount of time to terminate, every heuristic algorithm terminates within polynomial time and provide quick solutions, good solutions, and close to exact solutions, though not exact solutions all the time. Therefore, it is necessary to look at heuristics for the travelling salesman problem, because so far all the exact algorithms that have been developed for the TSP run in exponential time, and therefore, it is necessary to look at heuristic algorithms that do not provide exact solutions or do not guarantee exact solutions, but provide good solutions that run in polynomial time. Now, there are different categories of heuristic algorithms or heuristic methods. Some of them are called construction heuristics, and the others are called improvement heuristics. Now, in this lecture series, we will see some construction heuristics as well as some improvement heuristics to the travelling salesman problem. Now, let us start the discussion with the first heuristic. Now, the first heuristic that we will describe is called the nearest neighbourhood search. It's called the nearest neighbourhood search. Now, let us provide a quick solution to the travelling salesman problem. Let us assume that the person starts at city 1. Now, when the person is at city 1, now we have to find out which is the next best place to go. Now, 1 to 2 is 10, 1 to 3 is 8, 9 and 7. So, we would assume safely that the person would go to the nearest neighbour, which means that place or city which is closest to where the person is at present. So, from 1 this person would go to 5, because 1 to 5 is the smallest number here. Now, from 5, now the person can go to, it is either 5 to 2 or it is 5 to 4, it could be any one of them. So, let us assume the person goes from 5 to 2. Now, from 2 it is 10, 10, 5 and 6, the smallest number being 5, this person will go to 4, and from 4 the smallest number is 2, but the person will not come back to 2, because 2 to 4, 4 to 2 will be a subtour. So, the person will try the next one, which is 5. Again it does not come, because 5 to 4 and back to 5 is a subtour. So, the only thing that is available is 3, and then the person comes back to 1. So, this is how the nearest neighbour works. You start with any city, preferably the first, and then find out the nearest city. If the nearest city does not give a subtour, then add it, otherwise find out the next nearest and repeat till you identify a city which does not result in a subtour, and add it, and repeat the procedure till all cities are covered. So, this will be the nearest neighbour solution when we start with city 1. Now, the value for this, let us call it as z. 1 to 5 is 7, 5 to 2 is 6, 13, 2 to 4 is 5, 18, 4 to 3 is 8, 26, 3 to 1 is 8, 34. Let us do the nearest neighbour with city 2. So, we start with city 2, and then from city 2 the person will go to city 4, because 2 to 4 is the smallest. Now, from 4 the person will go to 5, because 4 to 2 the person will not do, because it is a subtour. So, from 4 he will go to 5, and then from 5 the person will go to 1, and then the person will go to 3, and then come back to 2. Now, this will give z equal to 2 to 4 is 5, 4 to 5 is 5 plus 6 11, 5 to 1 is plus 7 18, 1 to 3 is 18 plus 8 26, 26 plus 10, 36. Repeat, 2 to 4 is 5, 4 to 5 is 5 plus 6, 11, plus 7, 18, 18 plus 8, 26, 26 plus 10, 36. So, different starting cities can give different solutions. So, we have already shown solutions when we start with city 1 and city 2, we may do it with city 3, we may do it with city 4, we may do it with city 5, and then choose the best out of these 5 possible solutions as the best one. If we do it with 3, we would start with 3, from 3 we would come back to 1, and from 1 we will go to 5, from 5 we can go to either 2 or 4. So, we go to 2 and then 4 and then 3 with z equal to 3 to 1 is 8, 1 to 5 is 8 plus 7 15 plus 6 21, 21 plus 5 26, 26 plus 8 is 34. So, from 4 we would do 4, 4 to 2 is the smallest, 2 to 5, 5 to 1, 1 to 3 and 3 to 4 with z equal to 5, 5 plus 6 11, 5 to 1 7 18, 18 plus 8 26, 26 plus 8 34, and from 5 we will do 5 to 2, 2 to 4, 4 to 3, 3 to 1 and 1 to 5 with z is equal to 5 to 2 is 6, 2 to 4 6 plus 5 11, 4 to 3 11 plus 8 19, 3 to 1 19 plus 8 27 plus 7 34. Let me repeat, 5 to 2 is 6, 2 to 4 6 plus 5 11, 4 to 3 11 plus 8 19, 3 to 1 19 plus 8 27 and plus 7 34. So, out of these 5 solutions we realize that 4 of them give value 34 and 1 gives value 36. We also realize that 1 5 2 4 3 1 is the same as 2 4, it is different from 2 4 5 1 3 2, but if we look at this solution 1 5 2 4 3 1 is the same as 3 1 5 2 4 3 and so on. So, effectively all these 4 happen to be the same solution, this is different. So, the best of them we could choose any one of them with value z equal to 34 is the solution obtained using the nearest neighborhood search. So, we say that this could be the solution obtained using the nearest neighborhood search. So, the nearest neighborhood search starts like this. We can start with any one of the cities, say city 1, find out the nearest neighbor. If the nearest neighbor is already there in the solution, leave it. Now, find out that neighbor which is not yet in the solution, which means it will not form a subtour. So, add the neighbor and proceed till all the cities are exhausted and we come back to the starting point. Repeat this for every city as we have shown here. So, with 1, with 2, with 3, with 4, with 5 and choose the best. Now, this is an example of a construction heuristic. The reason is we construct, we start from 1 and we slowly build or construct the heuristic till we get a feasible solution to the problem. Every one of these is a feasible solution to the problem. Just because we know already, we have solved this problem before, we know that 34 is the best answer, we may say that this nearest neighborhood search has actually given us the optimum. But we are able to make that statement because we know the exact solution or the optimal solution. Ordinarily, we wouldn't be able to say that we have reached the optimum, we wouldn't be able to do that. So, the best out of these possible ones is the heuristic solution that is given by this particular heuristic. Now, each one of these heuristic solutions is a feasible solution, each of these is a feasible solution, and actually provides an upper bound to the optimum. The one thing we may be able to say is the best of this being 34, 34 is an upper bound to the optimum. It is customary to use a notation if L naught is the length of the optimal tour to the travelling salesman problem, then every LH, every solution that is obtained by this LH is greater than or equal to L naught. That is the only thing we might say. In this particular instance, we may be able to say that we have got the optimal, that is because we know that 34 is the optimal. Now, we can quickly understand that the computational effort that is required to do this is far less than the computational effort that was required to do this branch and bound, and more importantly, it is possible to show that we only do a polynomial number of steps to get each one of these solutions. So, this would qualify as a heuristic because it runs in polynomial time, it provides a feasible solution and it provides a quick good solution to the problem. Now, the goodness of any heuristic has to be measured. At the moment, we may be able to say that the best value is 34, but how good is that 34? Now, we know that this LH being 34, let us assume that we do not know this L naught. So, what we now know is that L naught is less than or equal to 34 is what we know from this. LH represents the length of the heuristic solution, L naught represents the length of the optimal solution. So, LH is always greater than or equal to L naught because it is a heuristic. Now, we need to evaluate the goodness of this heuristic to find out how good this heuristic solution is with respect to the optimal. So, we can derive some expressions for LH by L naught which tells us the extent to which the heuristic solution can be bigger than the optimal solution. Now, such an analysis can be carried out. Now, the expression for LH by L naught for the nearest neighborhood search is given by this. LH by L naught is less than or equal to 1 plus log n to the base 2 by 2. So, where n is the problem size and the logarithm is to the base 2. Now, this shows that LH by L naught is less than or equal to a quantity greater than 1. Now, we are not going to derive the expression for LH by L naught here. However, for later heuristics, we will derive expressions for LH by L naught. Now, what does this expression tell us? For example, if n is equal to say 16, then 2 to the power 4 is 16. So, this will become less than or equal to 2.5. So, 4 plus 1 5 by 2. For example, if n is equal to 128, 2 to the power 7 is 128. So, this will become less than or equal to 4. So, this shows that if we have a matrix with size 128, the length of the heuristic solution will be within 4 times the length of the optimal solution. So, we also observe from this expression that as n increases, the goodness of the heuristic comes down. So, we also need to look at heuristics where either the goodness of the heuristic remains the same irrespective of the length, or we are able to get better expressions for this LH by L naught. So, those heuristics that we subsequently are going to see, heuristics such as twice around the tree heuristic and a heuristic using perfect matching, we will derive expressions to show that LH by L naught is less than or equal to 2 in this case, irrespective of the size of the matrix, and LH by L naught is less than 1.5 in this case, irrespective of the size of the matrix. So, in summary, the nearest neighborhood search is a very simple algorithm. It starts with a vertex, it goes through a set of all other vertex that are nearest, which are not yet covered, and then it picks up the best solution from among these. The nearest neighborhood search has a complexity of 1 plus log n to the base 2 divided by 2. In fact, the second construction algorithm that we will see is actually from here. This is the branch and bound tree that we saw in the previous lecture, which was used to get the optimal solution. Somewhere during the previous lecture, we even mentioned that this branch and bound can actually help us get even a heuristic solution. Now, let us go back to this branch and bound, and let us say we started with 32, then we branched here to get 34, then we branched here again, we got 34, again we branched here, and here we found out a feasible solution with z equal to 34. Now, this was a feasible solution with z equal to 34. Now, the moment we got a feasible solution here with z equal to 34, for this particular example, we were able to fathom this, this and this, so that there were no more nodes that were available, and we said that this is the optimal solution. If for a particular example that this one of these values happened to be say less than 34, for example, if this happened to be less than 34, then I said that we have to proceed from here till we get to the exact solution. Now, if we want to use this as a heuristic, then right here we have a feasible solution with z equal to 34. We could have just stopped here and said this solution by itself is a feasible solution, and therefore, this part of the branch and bound up to the point where we get the first feasible solution can be used as a heuristic solution. So, the second construction algorithm or construction heuristic that we will see is actually this portion of the branch and bound tree, where when we come to this point we get a feasible solution, and this feasible solution acts as a heuristic to the travelling salesman problem. So, again we would show this as a heuristic solution. We may even ignore all the left side nodes if we were using this only as a heuristic solution. The third heuristic solution that we will see, so let us to do that, let us look at the minimum spanning tree associated with this matrix. Now, let us apply the Prim's algorithm to try and get the minimum spanning tree associated with this matrix. We have already seen in earlier lectures that the Prim's algorithm or the Kruskal's algorithm can be used to get the minimum spanning tree. So, let us first get the minimum spanning tree. The smallest one is between 2 and 4. So, we could start with 2 and 4 with value equal to 5, which is the smallest one. Now, in order to do the Prim's algorithm, now we go back, we have put 2 and 4 here, we have 1, 3 and 5 here. So, 2 to 1 is 10, 2 to 3 is 10, 2 to 5 is 6, so minimum is 6, 4 to 1 is 9, 4 to 3 is 8, 4 to 5 is 6. So, we could take either 2 to 5 or 4 to 5 and then do it. So, we take 2 to 5 with value 6 here as the next one. Now, we go back, update this to 5 and bring this down to 1 and 3. Now, we have to find out which one is going to join the minimum spanning tree. So, 2 to 1, 2 to 3, 10 and 10 minimum is 10, 4 to 1, 4 to 3 minimum is 8, 5 to 1, 5 to 3 minimum is 7. So, 5 to 1 comes here with value 7. Now, 1 gets updated here, 1 gets updated here and 3 comes here. Now, 2 to 3 is 10, 4 to 3 is 8, so minimum is 8, 5 to 3 is 9, minimum continues to be at 8, and 1 to 3 is 8. So, we could either do 4 to 3 or 1 to 3. So, let us say we do 4 to 3 with 8. Now, this is the minimum spanning tree associated with this. Now, this has a length equal to 8 plus 5 13 plus 6 19 plus 7 26. So, I am going to call this as LMST is equal to 26. So, length of the minimum spanning tree associated with this matrix is 26. Now, what does this information give us? We have solved a minimum spanning tree, and how is this related to the travelling salesman problem? Now, let us take any feasible solution to the travelling salesman problem. So, let us take a solution 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1. Now, if we take this feasible solution, now 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 1. Now, the travelling, this is a feasible solution to the TSP with L is equal to 1 to 2 is 10, 2 to 3 is 10 20, 20 plus 8 28, 28 plus 6 34, 34 plus 7 41. Now, the first thing that we observe is this L is greater than or equal to L naught, because this is a feasible solution to the travelling salesman problem. L naught is the optimal solution to the travelling salesman problem. Now, every feasible solution to the TSP has 5 edges or n edges, while the minimum spanning tree always has n minus 1 edges. Now, if we remove any edge from this, any one edge from this, say we remove this, then we have 3 to 4, 4 to 5, 5 to 1, 5 to 2, we have a spanning tree. This is a spanning tree because this has 5 vertices, 4 edges connected, and there is a path from every vertex to every other vertex. The original matrix has 5 nodes, this also has 5 nodes. So, this is a spanning tree to this. So, removal of every edge, for any one edge from any heuristic solution gives us a spanning tree. Now, let us assume that we do not know the optimal solution, but the optimal solution also is made up of 5 edges, and therefore, removing one edge from the optimal solution would give us a spanning tree. So, if there is an optimal solution, which if the optimal solution has a length L naught, and if we remove an edge from this L naught, we get a spanning tree. So, let us call that L as L spanning tree. Now, the length L spanning tree should be less than or equal to L naught, because L spanning tree is one edge less than L naught. As long as all theseCij's are greater than or equal to 0, which means we do not have any negative numbers coming here, which is a very reasonable assumption, because this is either a cost matrix or a distance matrix or a time matrix, which means to go from I to j, we will only have to travel non-negative distances, non-negative times or non-negative costs. So, as long as theseCij's from this are greater than or equal to 0, every edge in L naught is greater than or equal to 0, and therefore, removal of one edge from L naught would give L spanning tree, which is less than or equal to the length L naught. Now, this is a spanning tree to this matrix, and this is a minimum spanning tree to this matrix. So, by definition, LMST, length of minimum spanning tree, has to be less than or equal to length of any spanning tree, because by definition this is the spanning tree with minimal length. So, we have L spanning tree less than or equal to L naught, L minimum spanning tree less than or equal to L spanning tree, which is less than or equal to L naught. Therefore, we could say that LMST is less than or equal to L naught, and length of the minimum spanning tree is therefore a lower bound to L naught. Now, here we may say that this LMST of 26 is a lower bound to L naught, and the optimum solution cannot be 26 or less. So, this is the relationship between the minimum spanning tree and the travelling salesman problem. LMST is less than or equal to L naught, and it is a lower bound to L naught is a very important result that relates the minimum spanning tree to the travelling salesman problem. Now, having obtained the minimum spanning tree, what we can do now is we duplicate the edges of the minimum spanning tree. We duplicate the edges of the minimum spanning tree and then try to write down the duplicated edged minimum spanning tree this way. For example, I start from 1, 5, 2, 4, 3, 1 to 5. I am just marking that I have consumed this edge. So, 1 to 5, 5 to 2, 2 to 4, 4 to 3. Now, I come back, I do 3 to 4, I come back and do 4 to 5, I come back and do 4, 1 to 5, 5 to 2, 2 to 4, 4 to 3, 3 to 4, 4 to 2, 2 to 5 and 5 to 1. Now, this way I have covered all the 8 edges of this. Remember that the minimum spanning tree will have 4 edges, and when we duplicate it we would get 8 edges. Now, this is called, this is the length of twice the minimum spanning tree, and I am going to introduce a new term. I am going to say that this particular graph where we have duplicated the edges of the spanning tree is an Eulerian graph, and therefore I am going to call this with a E, and I say LE, length of the Eulerian, will be the length of this, which will be twice the spanning tree, which is 52, because this is double the length of the minimum spanning tree. Now, what is this Eulerian graph or Eulerian circuit? Now, we will quickly see the definition of this Eulerian. An Eulerian graph is one where you can start with any vertex, go through every edge or arc once and only once, and come back to the starting vertex, which is what we did. We went through 1 to 5, 5 to 2, 2 to 4, 4 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1. It is also very easy to follow that if we take a connected graph and we duplicate the edges, you can always get an Eulerian circuit. And we can also understand that if we have a graph where the degree of every vertex is even, then it becomes an Eulerian graph. Now, what is the degree of every vertex? The degree of every vertex is the number of arcs or edges that are incident on this. If we take this, there are 2, which is an even number. Here there are 4, here there are 4, here there are 4, here there is 2. This happened because we duplicated the edges. Each one of the edges was duplicated. So, if you take a given graph and duplicate all the edges, we will get an Eulerian. Now, this Eulerian will have a length of twice that of the minimum spanning tree. Now, this is going to help us in some ways to get feasible solutions to the travelling salesman problem. How are we going to do that? Now, let us start with this 1 and let us move 1 to 5, 1 to 5, 5 to 2, 2 to 4, 4 to 3, and if I come back from 3 to 4, I get a subtour, again I get a subtour. So, I do 3 to 1. So, I do 1 5, 1 to 5, 1 to 5, 5 to 2, 2 to 4, 4 to 3 and back 3 to 1 is a feasible solution to the travelling salesman problem. Now, this has L is equal to 1 to 5 is 7, 5 to 2 7 plus 6 13, 2 to 4 13 plus 5 18, 4 to 3 18 plus 8 26, 3 to 1 26 plus 8 34. Now, is this the only feasible solution we can get? No, we can get many more feasible solutions. Now, we can do another thing here. You could start with 1 to 5, 1 to 2, 2 to 4, 4 to 3, 3 to 5 and 5 to 1. So, you could do 1 to 2, 2 to 4, 4 to 3, 3 to 5, 5 to 1. This is another solution you can get. Remember, the way what we do is we keep moving like a nearest neighbor, but we look at several different solutions and make sure that we create tours as we move along. So, 1 to 2 is 10, 2 to 4 is 5, 15, 4 to 3 is 8, 23, 3 to 5, 23 plus 9, 32 and 5 to 1 is 32 plus 7, 39. Repeat, 1 to 2 is 10, 2 to 4 is 5, 15, 4 to 3 is 8, 23, 3 to 5, 9, 32, 5 to 1, 39. Now, we can do one more solution like this. We could do 1 to 4, 4 to 3, 3 to 2, 2 to 5, 5 to 1. So, we could do 1 to 4, 4 to 3, 3 to 2, 2 to 5, 5 to 1. L is equal to. Now, 1 to 4 is 9, 4 to 3 is 9 plus 8, 17, 3 to 2, 17 plus 10, 27, 2 to 5, 27 plus 6, 33, 5 to 1, 33 plus 7, 40. So, we got another solution with 40. Now, we can do one more here. We could do 1 to 3, 1 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1, 1 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1. 1 to 3 is 8, 3 to 4 is 8 plus 8, 16, 4 to 2, 16 plus 5, 21, 2 to 5, 21 plus 6, 27, 27 plus 7, L is equal to 34. Now, we can do one more thing. We can go from 1 to 4, so we could do 1 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1. So, you could do 1 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1 and L is 1 to 5 is 7, 5 to 4 is 7 plus 6, 13, 4 to 3, 13 plus 8, 21, 3 to 2, 31 plus 10, 41. Compute again, 1 to 5 is 7, 5 to 4, 7 plus 6, 13, 4 to 3, 13 plus 8, 21, 3 to 2 plus 10, 31, 2 to 1 plus 10, 41. So, like this it is possible to evaluate as many solutions through this. The only condition being we have to, at the end of it, we should be able to move in this and then come back to 1. We should not move backwards. We should only keep moving forward and try to get as many solutions as we can. We should not move backwards. For example, we cannot do this. We cannot do, for example, 1 to 4 or 1 to 2, 2 to 4, 4 to 3, 3 to 5, 5 to 1 we should not do, because we would have moved backwards. So, in this type of a heuristic algorithm, after we get this, you could go back and evaluate as many solutions as you can from this and then take the best. In this example, the best happens to be here as well as here, which gives us the best solution is 1, 5, 2, 4, 3, 1 with L equal to 34. Now, here also we have got the solution with L equal to 34, but then unless we know that it is optimal through some other means, we cannot say that it is optimal. We would now provide this as a heuristic solution. Of course, we know earlier that this is the optimal solution. So, this particular heuristic gives us a solution with L equal to 34. Now, this heuristic is called twice around the tree heuristic. It is called twice around the tree heuristic. And is a very popular heuristic from the literature. It is also easy to understand why it got its name, because in this heuristic the most important step is to compute the minimum spanning tree and then duplicate it and then get this. So, it is like moving around the minimum spanning tree twice, and therefore, it is called twice around the tree heuristic. Now, we have to find out, can we possibly find out a good analysis of this? How good is this heuristic? We saw earlier that a goodness of a heuristic is given by this expression called LH by L naught. Now, what is the expression for LH by L naught for this particular heuristic? So, let us try and get that expression for this particular heuristic. Now, the first step of this heuristic was the computation of the minimum spanning tree. So, we computed LMST. We also said earlier that LMST is a lower bound to L naught, because removal of any edge from L naught would give us a spanning tree, and LMST is less than or equal to L of any spanning tree. Therefore, LMST is less than or equal to L naught. Of course, this is under the assumption that all Cij's are greater than or equal to 0. So, under the assumption that all costs are non-negative, LMST is less than or equal to L naught. What we did here was, we found out another LE, which is called the L Eulerian, and this Eulerian was obtained by duplicating the edges of the minimum spanning tree. So, we got the minimum spanning tree here, and then we duplicated the edges and we wrote all the 8 edges in a certain order. So, L Eulerian we already mentioned is 52, which is twice LMST, because the L Eulerian is obtained by duplicating the edges of the MST. So, we have L Eulerian is 2 times L MST. Now, the next thing we did was, from this L Eulerian we picked up several solutions, each of which is a heuristic solution to the TSP, and we found out the best out of that. So, let us take the best out of that, say, which is this 34, and we call this as LH. But every LH, length of every heuristic, every LH, we will show that this will be less than or equal to LE. How? If we take this, how did we get this solution? This is 1 5 plus phi 2, 2 4, 4 3 and 3 1. Now, 1 5 is common, phi 2 is common, 2 4 is here, 4 3 is here, but this heuristic has 3 1, whereas LE has 3 4 plus 4 2 plus 2 5 plus 5 1. Now, if this distance matrix satisfies triangle inequality, which means any Cij is less than or equal to Cjk plus Cki. If we do that, if the given matrix satisfies triangle inequality, then 3 to 4 plus 4 to 2 is more than 3 to 2. So, 3 to 2 plus 2 to 5 is more than 3 to 5, and 3 to 5 plus 5 to 1 is more than 3 to 1. Therefore, 3 to 4 plus 4 to 2 plus 2 to 5 plus 5 to 1 is more than 3 to 1. Therefore, you will see that LE is greater than or equal to LH, from which LH is less than or equal to LE. So, for every one of these solutions, which we may call as LH, if the matrix satisfies triangle inequality, then LH is less than or equal to LE. Even if we take something like this, if we take 1 to 5, 5 to 4, say before let's take this. So, we said 1 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1. Now, 1 to 5 plus 5 to 2 plus 2 to 4 plus 4 to 3 is greater than or equal to 1 to 3 by triangle inequality. Therefore, the LH corresponding to this will be less than or equal to LE. If we take this 1 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 5, 5 to 2 plus 2 to 4 is greater than or equal to 5 to 4, 4 to 3, 3 to 4 plus 4 to 2 is greater than or equal to 3 to 2, and 2 to 5 plus 5 to 1 is greater than or equal to 2 to 1. Therefore, this LH will be smaller than LE, or LE is greater than or equal to this LH. So, LE is greater than or equal to every one of these that is here, and therefore, LE is greater than or equal to the best of these, which we call as LH. Since LE is greater than or equal to every one of these, it has to be greater than or equal to the best of these. So, LE is greater than or equal to LH, or LH is less than or equal to LE. Now, LE is equal to 2 times LMST. So, this is less than or equal to 2 times LMST. Now, from this result LMST is less than or equal to L naught. So, LH is less than or equal to 2 L naught. Now, from this we can derive LH by L naught is less than or equal to 2, which is an important result about the performance of the twice around the tree heuristic. Now, this heuristic we can say with confidence that this heuristic will guarantee a solution always such that the solution LH by L naught is less than or equal to 2. No matter what the problem size is, we will get LH by L naught less than or equal to 2, provided all theCij's are greater than or equal to 0, and this satisfies triangle inequality. So, under these two conditions, we can say that twice around the tree heuristic, no matter what the size of the problem be, no matter what the numbers are, as long as those numbers are real numbers and they satisfy triangle inequality, we can say that LH by L naught is less than or equal to 2. So, this is some form of an analysis of a heuristic, and this is a construction heuristic because we have constructed the solution, the heuristic solution from this. So, this is how the twice around the tree heuristic works. It is called twice around the tree because we go through the minimum spanning tree twice. It also has a performance measure of 2. Now, we look at another heuristic which is also based on the minimum spanning tree. Now, we have already seen that this is the minimum spanning tree. So, 1 to 3, 2, 3 to 4, 4 to 2, 2 to 5 and 5 to 1. Here we have duplicated it. So, I am just removing this and we say this is the minimum spanning tree with values 3 to 4 is 8, 2 to 4 is 5, 2 to 5 is 6 and 1 to 5 is 7 with LMST is equal to 26. 8 plus 5 13 plus 6 19 plus 7 26. Now, let us look at the minimum spanning tree and let us look at some properties of it. This is a graph which is a collection of nodes and arcs. Now, with any graph there is an interesting property that the number of vertices with an odd degree is even. Now, let us explain this. Now, what is the degree of a vertex? The degree of a vertex is the number of edges that are incident onto the vertex. Now, this has a degree 1 because there is only one vertex, this has degree 2, this has degree 2, this has degree 2 and this has degree 1. Now, since every edge is counted twice because every edge connects 2 vertices, so it contributes the degree of 2 vertices. So, the total degree of any graph is an even number because it is multiplied by 2 times the number of edges. So, the total degree being even, it is obvious that the number of vertices with odd degree will have to be even. So, in this example there are 4 edges in this. So, sum of the degrees has to be 8. We will see 1 plus 2 plus 2 plus 2 plus 1. So, we got 1 plus 2 plus 2 plus 2 plus 1. This is odd degree, this is odd degree. So, number of vertices that have odd degree will have to be even. So, that is true with any graph, and therefore, it is true with the minimum spanning tree as well. Now, find out the number of vertices that have an odd degree. In this case, it is just 1 and 3. There are 2 vertices that have odd degree, which happen to be 1 and 3. Now, if you have only 2 vertices that have odd degree, then just go back and join the vertices. Just join the vertices and you add another 8. So, we said if you have only 2 vertices that have odd degree, the only thing that you will do is you will simply join these 2. And when you simply join these 2, you will get one solution which is a circuit, because you have simply added one edge into a minimum spanning tree. If you have only 2 vertices that have odd degree, then you will simply put this into the spanning tree, just add it to the spanning tree. So, and you also realize by adding such a vertex, you get one more Eulerian, which means you can start from 1, 1 to 5, 5 to 2, 2 to 4, 4 to 3, 3 to 1. You go through every edge once and only once, and you come back to the starting point. It is also Hamiltonian that from every vertex you can go to every other vertex and come back to the starting point. So, in this case the L Eulerian will be equal to L MST plus some L that we have added. So, I am just going to call it L add, and because the number of vertices having odd degree is only 2, so we just end up adding only one edge into this solution, and therefore, this solution is 1 to 5, 5 to 2, 2 to 4, 4 to 3, 3 to 1. There is only one solution that you get here if you have 2 vertices coming here. So, you get only one solution. Now, the length of this solution is 1 to 5 is 7, 5 to 2 7 plus 6 13, 2 to 4 13 plus 5 18, 4 to 3 18 plus 8 26, 3 to 1 is 34. There is only one solution which we give as a heuristic solution. So, LH is equal to 34. Now, we have provided a heuristic solution to this problem whose length is equal to 34. Now, this algorithm is called heuristics based on matching, but let me explain the matching as well. Based on matching, but let me explain the matching differently. We have seen only one case where the number of vertices with odd degree happened to be 2. So, when the number of vertices with odd degree happens to be 2, we simply add that particular edge into the spanning tree to get a feasible solution to the travelling salesman problem, which becomes your LH. But what happens if you have more than 2? For example, if the minimum spanning tree for a 5 city problem say is like this, let us say with 1 here, let me say 2, 3, 4 and 5. Now, this is a case where the number of vertices with odd degree is 4 as against number of vertices with odd degree equal to 2. Now, in this case you have to go back and create. Now, the vertices with odd degree are 2, 3, 4 and 5. So, you will create now from this another matrix with 2, 3, 4 and 5, 2, 3, 4 and 5. This is assuming that 2, 3, 4 and 5 are the vertices with odd degree. So, create this matrix. So, we would get a matrix which is like this dash 10, 5, 6, we would get this portion of the matrix 10 dash 8 9 9 5 8 dash 6 6 9 6 dash. So, we would get a matrix like this. Now, what we have to do from this matrix is to get a minimum weighted matching. Now, what is this minimum weighted matching? Now, there are 4 nodes 2, 3, 4 and 5. Now, for example, if I take 2 to 3 and 4 to 5, it is called a matching, because there are 4 nodes. I have created 2 edges such that the nodes are not common, but all the vertices are included. So, if I look at 2, 3, 4 and 5, I may have 2, 3, 4, 5, I may have 2, 4, 3, 5 and I may have 2, 5, 3, 4. Now, because there are 4 vertices, there can be only matchings, 2 matchings. Each matching has 1 edge and 2 nodes. If we take this particular matching, this matching comprises of all these 4, 2 edges, but all 4 are kept here. So, 3 such matchings are possible and the weights of these are 2, 3, 4, 5 is 16, 2, 4 is 5, 3, 5 is 5 plus 9, 14, 2, 5, 3, 4 is also 14. So, out of the 3 possibilities that we have here, the minimum one is either this or this. So, we could choose any one of them, choose the minimum weighted matching and then add it on to this. Suppose we take 2, 4, 3, 5, then we end up doing 2, 4, 3, 5 on to this and then we will get a solution 1 to 2, 2 to 4, 4 to 1, 1 to 3, 3 to 5, 5 to 1. This will be the L Eulerian if you superimpose this. We continue the discussion on this in the next lecture.